Welcome everyone, welcome to Academy. Today we will continue our lesson on Schrodinger equation. Okay, so first we'll learn about the commutators. Okay, so now we have seen that every observable in quantum mechanics has an operator. Okay, so for example, energy has an operator, momentum has an operator. Similarly, position has also is also an operator. Okay, whose eigenvalue gives the position of a particle. Okay, so if x is a position operator and px is a momentum operator, okay, along x direction, then we can calculate the following expression, okay, which is x px minus pxx, which is acts on psi. Now, if we substitute the operator form of momentum, which is minus I h over del del x, so we'll get this. If we calculate this one, we'll get x px minus pxx psi is I h bar psi. Okay, see that this is also an eigenvalue equation, which means that this thing is also an it's also like an operator, okay, whose eigenvalue is I h bar, which acts on psi. This is the eigen function. Okay, now since psi is an arbitrary function, we can write x px minus pxx. It is written as third bracket x comma px, okay, which is I h bar. Okay, this is known as commutation relation. Okay, we'll know more about this commutation relation in the later course, what it means actually. Okay, if you want to, if I just say that I'll say that this means in quantum mechanics that you cannot really measure the position and momentum of a particle simultaneously. This is what it means actually, but I'll explain more on commutators later on. Okay, let us first see some of its properties. So if alpha and beta are the two operators, then alpha beta is alpha beta minus beta alpha. So if we just switch this position of alpha beta, it will be beta alpha commutator, which is a minus with a minus sign. Okay, the commutator, when it switches, it comes with a minus sign. Okay, so it is easy to show that xy, all these commutators are 0. Okay, but ypx, ypy and zpz is I h bar similarly. Okay, so which means that in the x direction you cannot measure the position of a particle and momentum simultaneously. Similarly for y direction and z direction. Okay, now let us see some physical interpretation of psi. Okay, now this is the Schrodinger equation. Okay, now we assume that b is real quantity. Okay, so if we take its complex conjugate, we'll get this. Now multiply this by psi star and multiply this by psi, and then if we subtract, we'll get this equation. Okay, this is a very simple algebra. If we look at this equation carefully, we'll see that this equation we can make it in this like this form. Okay, which is a I h bar so del del t psi star psi plus del jx del x del jy del y del jz dz equal to 0, and this thing can be given. This thing is given by these equations. Okay, now from here to here you will need this algebra, which is very easy in which is very common in vector calculus. Okay, if we use this formula here, you will get this equation very easily. Okay, provided jx jy jz is given by this. Now the current density. Okay, now this is the equation what we have got. Okay, so we can write this equation as del rho del t plus divergence of j. Okay, this is certainly a divergence. Okay, so where rho is psi star psi and j is I h but 2m psi delta psi star minus j psi star delta psi. Okay, this is in 3 dimension. So This is called probability position probability density, and this is called probability current density. Okay, if we calculate this quantity, which is integral psi star psi d tau, which is the volume integral. Okay, uh, this is, you can also do it in one dimension, there is no big deal. So if you take its time derivative, so this is this probability density. Okay, so del rho del t d tau, and now if we use this equation we'll get this, and using the Gauss divergence theorem we'll get this. Okay, now if we integrate over the entire space and assume that the wave function vanishes at infinity, then the right hand side in this quantity will be 0. Okay, because j is this, if psi is 0 then j is also 0. So what we will get, we'll get del t volume integral of psi squared d omega, d tau is 0, which is the conservation condition. Okay. So now the statistical interpretation, that we have been saying that in quantum mechanics a particle is represented by a wave function. Okay, now you might think that what is this wave function actually. Okay, how this wave function is spread out in space can possibly represent a particle which is localized in space. So the answer is given by the statistical interpretation by Max Born, which says that psi star psi represent the probability of finding a particle at position x and t, and more precisely it is given by integration a to b psi star psi del psi star psi squared dx is the probability of finding a particle between a and b. For a volume integral, this will be for a 3 dimension. In 3 dimension, this will be a volume integration. So now, where was the particle before measurement? Okay, actually this is a very ambiguous question in quantum mechanics. This means this thing means that if we consider a region between a to b, there is some particle. Okay, depending on its value. Okay, so now it's a very interesting question in quantum mechanics, that where was the particle before measurement. And because we say that a particle is described by a wave, so it's actually spreaded over the space. Okay, now an act of measurement forces this wave to collapse to a particular position, and this gives, and that's where we find the particle after, if we carry out a measurement on the system. Okay, this might look bizarre, this might sound really bizarre, but this is what quantum mechanics says, and you can understand this by a very similar experiment which I told you before. This is the double slit experiment by electron. Okay, so here are some um, uh, facts about this experiment. I'm not going to explain this experiment again because I have done this before. So I'll just state some facts about this experiment, and I'll try to make it clear that why I just made the statement that you cannot predict the initial condition of a particle in quantum mechanics. I mean, where was the particle before experiment? We cannot actually really answer this question. Okay, so quantum mechanics cannot predict the precise location of each electron in this experiment. Uh, all it can tell the probability of landing an electron in a particular position. If we close one slit, then the fringe pattern disappears. Now, this is an act of measurement. Okay, we want to know that through which slit the electron passes. Okay, so if we do that, this fringe pattern will just disappear. Okay, so an act of measurement of course disturbs the system and forces it to take a particular position. So what if we do not interrupt with the system? Okay, if we do not interrupt the system, which means if the both slits are just fine and it is open, so the electron as a wave passes through both the slits and interfere with itself and gives us a pattern like this. Okay, just like a wave. Okay, if you really want to visualize this experiment, there is a very beautiful video by this YouTube channel Arvin Ash. You must check it. Okay, he explains this experiment very beautifully with animation. You can just see and check it. Okay, now normalization and expectation value. So normalization of a wave function is defined as minus infinity to plus infinity psi square dx equal to 1. Okay. Solution of Schrodinger equation gives a solution with a multiplicative constant a. Now any differential equation you solve, it comes with a constant. Okay, so the constant where this constant is basically complex number, and the above integral shows that we can adjust this constant in such a way that this integral is equal to unity. What it means actually by normalizing a wave function, it means that here the limit is minus infinity to plus infinity, but for a bound state, or more precisely for a system with finite dimension, this will be some certain limit. So if we normalize this equation with 1, we say that within that system there is only one particle. This is the physical interpretation of normalization. Okay, since we know that we have seen that psi squared, which means psi star psi, is the positional probability density. So of course square of that integrated over the space gives us the number of particles. Okay, if the solution is infinite and zero or no multiplicative constant can make the integral equal to 1. Okay, and these are called non-normalizable solutions, and thus and it cannot represent a particle. So what is the basic criteria for a particle, for a wave function to be represented a particle? So a physically realizable state corresponds to a square integrable solution of Schrodinger equation, which means that the wave function vanishes at infinity. Okay, so this is the condition for that. Del t psi star d sigma equal to 0, and del ddt is minus infinity plus infinity psi square dx equal to 0. So now this is the normalization. Okay, this is the normalization equation. So if the time derivative of this normalization equal to 0 means that once the function is normalized, it's normalized in future. Okay, this is very common. This is very easy to understand because I have told that this equation, this normalization means that we have fixed uh, only one particle in a finite dimension or in a finite system. We have contained only one particle, so it is not desirable that over the time the particle leaves that place. Okay, so we see that this condition reflects this equation reflects that condition. Okay, okay. Now the expectation value. So the expectation value is defined as f of r if f is a operator, a quantum mechanical operator of an observable. Okay, it is defined as integration phi star fr psi d tau. Okay, this is the volume element. Okay, so for position we'll write psi star psi x d tau. For energy we'll write psi star I h by ddt psi d tau, and for momentum we'll write triple vector triple integral. Here it is not here it is also a vector integration, but triple integration sign is not there, but it's a volume integral. Okay, okay, so this is also a volume integral psi star minus I h bar del psi del x d tau. Okay, so what it means by expectation value, The expectation value is the average of measurement on an ensemble of identically prepared system. This is a very complex statement, so I read it out once again. The expectation value is the average of measurements on an ensemble of identically prepared system, not the average of repeated measurements of one and the same system. Why it is so? Okay, remember I told you that we cannot really say with 100% accuracy that before measurement where was the particle. Okay, so the initial condition, the initial state of the particle could be anything. Okay, and an act of measurement forces the particle to stay in one place. Okay, it really, so the before the measurement, the wave function was spread over the position. Okay, so when we try to measure the position of a particle, then only the wave function collapses to a particular position and gives us the result that okay, we have found a particle here. Okay, so that's why we cannot predict the actually the initial condition, initial state of the particle, so we cannot really know. So what will happen if we just take one system with one particle and try to measure its position over and over again? Okay, so because it was spreaded over initially it was spreaded over uh, over the space. So if we want to uh, make a second measurement, okay, we cannot really know. We have to find a, first we have to fix the initial condition. Okay, so if so in an experiment, in our general knowledge, when we do an experiment, if we want to make an average, if we want to make an average result, what we do, we repeatedly measure that quantity, which means we take a measurement, we then we get back to our initial I mean position from where we started measuring, and then we take another reading. Okay, and we repeat this in a number of times, and we take their average. So every time we we know that where we came from, so we can get back to that position, and we can perform that experiment again, and the experimental result could be different for different times. So here the one thing is fixed, that our initial condition, the initial state is the fix, but in quantum mechanics there is nothing like initial state. The particle initially was everywhere, you can say. Okay, there was not a fixed position for the particle. Okay, that's why mathematically we say that what we can do, we can create an ensemble of infinite number of identically prepared system. Okay, so the particle was, will say that the particle was somewhere between, the identical system, and if we measure that position all the systems at equal time, okay, simultaneously, then this is the outcome of that experiment is this. If you measure the position, it is this. If you measure the energy, it is this. If we measure the momentum, it is this. Okay, so this is physically, we want to just, if we want to understand it physically, then this is it. So we cannot repeatedly measure on the same system. We have to take an infinite number of infinitely large ensemble of identically prepared systems, so to measure a quantity, measure an observable. Okay, mathematically you can say that this is an operator, and this operator acts on this wave function psi, and this will give us a eigenvalue, okay, which is just a constant, so it will go out of the integration, and the integration will only consist of psi star psi integrated over the volume, which is 1. So it will give us some value for a particular state. Okay, we'll use this concept later. So this is it for now. Thank you. See you in the next class.